Okay. All right, Chem 1311 Exam 1 review. Can everyone see my screen?
Yeah.
Okay, cool. All right, so the first quick thing we want to get through is atomic theory. So just a quick foundation is basically the idea behind atoms and atomic theory kind of started back in 5th century BC by the philosopher Democritus. He was pondering like how small you could make divisions until you can no longer cut something in half anymore. And he considered that like the smallest particle, so he called it an atomos. And he says that matter was created by basically a bunch of small invisible particles. And then fast forward until like many centuries later, we had this guy named John Dalton, and he started laying more ground rules behind what matter and atoms are. So he basically stated that all matter is composed of atoms, and that all atoms of a single kind of element are identical. Not everything he said was true. If you guys remember, isotopes are another variation of an atom, but they are not identical to other isotopes of the same atom. Dalton also stated that compounds have atoms of more than one element, so you can have combinations. And in these compounds, the atoms are put in a fixed ratio. And he also stated that atoms are indestructible and that all chemical reactions are simply rearrangements of different atoms. And then there's some famous scientists, 3 in particular, I should keep in mind. There's J.J. Thomson, and he was credited with the discovery of the electron, and he created one of the first models of the atom called the plum pudding model, which would be built upon by Ernest Rutherford, and he helped discover that the atom was mostly empty space with a dense nucleus, so he kind of disproved the plum pudding model. If you guys remember, the plum pudding model is old kind of food. It's like basically a treat. It's kind of like a hard fruit cake, and there's like little pieces of fruit within it, and that's what he thought an atom would look like. But it turns out that was not the case. And finally, Niels Bohr, he helped discover that the electrons that were eventually discovered later lie in quantized energy levels, so they don't all lie within the same energy level. They lay in different layers, basically. Okay, we're going to go talk about the structure of the atom. All right, quick overview of electrons and how they were discovered. So one of the first experiments performed by J.J. Thomson was a cathode ray tube. So the idea behind a cathode ray tube was that a ray of particles were leading from a tube from the cathode to an anode. It's very similar to one of the old neon signs that you guys could see maybe in like movies or in the street. But yeah, it's just a beam of light, and then he applied electric fields to those beams. The scientists at the time knew there were particles inside, but they didn't really know much about the particles. And whenever he applied the electric field, when he applied a positive electric field, the particles moved towards the electric field. And he reapplied the negative electric field, the particles moved away from that. So basically, he discovered that those particles were charged, and they were negatively charged, right? Because like repels like. And basically, he also knew that those particles were even smaller than an atom. So he kind of discovered the existence of electron. And building on that, the oil drop experiment. So Robert Milken wanted to measure basically what the charge of the mass of an electron was, and so he put a negative charge on a piece of oil, and he had to put it into an electric field to see how strong the electric field needed to be to stop the oil from falling. And so from that, he was able to extrapolate and discover the mass, calculate with the mass of the oil to get the charge of that drop. Okay, move on to the proton and nucleus. All right, so again, referring back to Thomson, he helped create the plum pudding model, so he wanted to explain how atoms are neutral. So he thought that since there has to be positive charges within the atom in order to negate the negative electrons to make the atom overall neutral, right? And so he thought the atom was basically a sphere of positively charged matter with electrons throughout it. Oh, skipping. Okay, and one of the other scientists later on down the line, he performed the gold foil experiment because he wanted to test Thomson's theory about the plum pudding model. And so in the gold foil experiment, he basically shot alpha particles at this gold sheet, right? And the idea is kind of similar to the fact that it's kind of like a thin piece of paper, so the particles should have just gone right through. It's kind of like shooting a piece of paper with a shotgun, and so you're getting all the shot to go right through the page. But in some cases, some of the particles actually ricocheted off the foil and they bounced into the sides. Sure, you can still get the image over here. Is basically it recoiled and it hit a detector. And so he thought that was very strange, and he eventually came to the conclusion that the plum pudding model was incorrect and that the atom had to be mostly empty space because most of the particles went through the gold foil, so there has to be a lot of empty space. But there has to also be solid, dense areas where the ricochet can occur. And so he concluded that the atom had like a dense positive nucleus, but it was mostly empty space. Okay, and so the neutron. The discovery for the neutron was Sir James Chadwick. He shot a beryllium atom with a bunch of alpha particles, and he found there was uncharged radiation that was emitted. So since it was neither positive nor negative, it's neutral, he called it a neutron. So a summary from all three of these slides, basically there's protons and neutrons that are in the nucleus, and electrons are found in a cloud circling the nucleus, and the neutral atoms have the same amount of protons to electrons. Okay, so I'm going to go through atomic numbers and atomic mass real quick. All right, so every element, as you know, has a unique atomic number. So looking at this model here, A, X, and Z. So your atomic number Z is the number of protons you have. So that identifies what element you are, right? Every element has an exact number of protons. However, mass number is going to differ a little bit. So mass number A is representative of the number of neutrons and protons. But as you guys know, not every element or not every atom has the same number of neutrons as its sister element. There are variations in atoms called isotopes where they have the same Z, so same number of protons, but different number of neutrons. They will have identical properties, though. So they're almost basically the same element in size, maybe 1, 2 more neutrons. Okay. And then atomic mass scale. So you guys probably have seen weighted average problems. So on the periodic table, the number beneath each of the elements is considered the weighted average of the isotopes of each element. So when scientists conclude the weight of an element, they want to look at the relative abundance, about how much percent of oxygen has this certain amount of weight. And how much percent oxygen has that amount of weight, and so they kind of average it together. So they take like 10% of oxygen has this, like 16 grams per mole, and then like 90% has 16.5 grams per mole, something like that. They average them. And then their scale, since these atoms are very, very tiny, we call them atomic mass units, and an AMU can be defined as 1/12 of the mass of a carbon atom. Okay, and then just a quick brush through of the periodic table groups. Right, so periods are basically the horizontal rows. They have the same energy level and the same valence shells. So you're looking at the rows. And columns are also considered families, or the vertical groups. And these guys are going to have the same chemical and physical properties. And they should also have the same number of valence electrons. They won't have the same number of energy levels or shells, but they'll have the same number of valence electrons. And so coming down to different types of like areas or groups on the periodic table, if you guys remember, looking at the periodic table on the slide, you can see the yellow zigzag kind of line. That is the division line between metals and non-metals. So metals are going to be to the left of that staircase, basically, and metals are good conductors of heat and electricity. As you know, they're shiny and they're considered malleable. That means you can shape them to whatever you like. Non-metals are going to be to the right of the staircase, and those guys are almost the opposite of metals. They're going to be non-conductors. They're very bad at conducting electricity or heat, and they vary in different kinds of color, and they're usually not shiny. They're kind of brittle as well. They can break easily. Okay, and so metalloids, that one line, that one zigzag line, right? So they're kind of like between metals and non-metals. They have some properties of metals and some properties of non-metals. So you just have to know that they're in between. And then transition metals. So they're that column that's blue elements. So they basically have incomplete inner subshells. And the unique thing about the transition metals is that they can have different charges on the same element. So some elements can have two or three kinds of charges. And just listing like the specific names for some of these columns or vertical groups. So you can have group 1 that's known as the I metals. Group 2 is the alkali earth metals. Group 6, starting from, it's oxygen, right? Yeah, those are considered the chalcogons. And then the group to it, starting with fluorine, is the halogens, and then the group to the farthest right are considered the noble gases because they don't really interact. They are fairly stable by themselves. All right, so going over moles and molar mass real quick. All right, so what is a mole? You guys have probably seen this down already, but again, a mole is a group of measurements, and a mole is considered 6.022 times 10 to the 23rd power. So it's a group of items, just like a dozen or a baker's dozen, something like that. So this number is also considered to be Avogadro's number, since he helped put emphasis and establish that to be a significant number. Interestingly, it represents the number of atoms that are in 12 grams of carbon-12. So basically, 1 mole of carbon-12 is equal to 12 grams. And so this is a way that you can relate mass to moles. So taking a look over here to the right of the picture, we can see this little diagram. It's very important you guys are able to understand this diagram. Just let us know whenever we get to the practice problems if you guys are having trouble with that diagram at all. So this allows you to interconvert between grams, which is mass, moles, and then atoms, using Avogadro's number or molar mass.
All right. Can you? Yeah. All right. So before I start my part of the presentation, I just want to tell everyone that we're here to help y'all. We're really sorry that we can't do this in person. Like, it's so much easier to present all this information for you guys in person, but unfortunately COVID, but we're gonna do our best. And I completely understand all of y'all's stress and concerns, because this is, a lot of y'all are first semester freshmen, and um, so it's your first like really big exam of college, so this can be really tough. So just continue asking questions. You guys are asking great questions. Kevin, could you continue sharing your screen?
Oh, I would need to monitor the chat on my computer, so I was wondering if you could.
I'm on my iPad, so I'm not able to
Oh,
share.
okay. Okay, that's fine. I can continue
I think
sharing.
the other computers will be fine monitoring the chat.
Okay, cool.
Yeah.
Right, 1 second again. Okay.
All right, so I'm gonna start, and I was asking my session yesterday, what's your biggest concern? What's your biggest, like, what are you scared of most for this exam? And a lot of them were saying that they're worried about the equations, and when do I use which equation? And that's really tough. It's hard to know. Okay, you read a problem, and some people might instantly know what equation to use, but that's not so easy for some people. So I'm gonna go over all the equations y'all need to know, and how maybe you can like easily figure out what equation to use for which problem. All right, so next slide. Yeah, so I just want to start off talking about light. So light is a wave. And whenever you look at light now, I want y'all to think of it as a wave. And when you have different colors of light, you might notice some light is red, some light is more blue. Different light has different energy. And so when you look at these waves, they have different wavelengths. And you can see a wavelength is the distance from one peak to another peak. So,
Sorry. Yeah, my laptop has kind of issues with the keys, so it kind of like bounces every once in a while.
that's okay. So you can see that the A wave, the A,
Oh gosh.
the
Okay,
A wave,
sorry.
which is red, it has a longer wavelength than the blue wavelength on C. So what does that mean? That means that the longer wavelength actually has less energy than that bottom wavelength of the blue light. And so how do I remember this? How do I remember that different light has different energies, different wavelengths may have different energies? I think of, if you guys have ever seen fire, really, really hot fire is typically blue, while like the less hot fire is like orange or red. So what that tells me is, hey, blue light or blue fire is more, warm or hot. So that has more energy than red fire. So what I realized is, okay, that means that red light has a longer wavelength than blue light, and so that it tells me that it's you can kind of think of the wavelength as being slow and long, and so it has low energy, whereas the blue light, which is really, really fast like that, has a high energy. And so yeah, I see in the chat that you guys are talking about Rho G Biv. You can think of it as red, orange, yellow, green, blue, and so on, with increasing energy. So red has the least energy, blue has the most energy. And so with this concept, we have an equation that tells us the speed of light, which is c. Speed of light, c, which is 3 times 10 to the 8th, is one of the 4 equations that you guys should have memorized. Speed of light equals the wavelength, which is, like I said, the peak to the peak, times the frequency, which is how often does that wavelength occur. And that's going to give you speed of light, which is meters per second. What is the unit of a wavelength? It is a distance, so it's meters, or typically nanometers. And what is the unit of a frequency? It's seconds in meters. And so when you combine that, you get meters per second. One more thing that I want to talk about on this slide is something important called the photoelectric effect. The photoelectric effect is it's like this concept in which let's consider that I have an atom, and that atom is gonna absorb some energy. So let's say the atom absorbs some energy, and what happens to that electron that's on the lowest energy level of that atom? That electron, after it absorbs some energy, it may jump to a higher energy level. It might say, oh, look at all this energy, I'm going to jump to a higher energy level. Well, what if that atom absorbs so much energy at one time that that electron just goes crazy and it just ejects out of the atom? What happens then is something called the photoelectric effect. And what that says is the absorption of electromagnetic radiation, aka a fancy word for light or energy. Anytime that's absorbed in an amount that's enough to eject an electron, that's the photoelectric effect. And um, that's pretty important. They usually ask a question about the photoelectric effect, kind of what it is. And so yeah, you can go to the next slide. So I've kind of touched on this a little bit, light and the electromagnetic spectrum. You can see that the higher energy that you have is at the gamma ray side. So gamma rays have very high energy with X-rays and UV light. Then you see the light that we can see, you and I can see, that's visible light. And we see that violet light has the highest and red light has the lowest. And then you go infrared, microwave, radio wave. There's an acronym for this somewhere. Maybe if someone knows it, they can put it in the chat. But I can't remember right now. But this is something that you guys should probably know, like, you know, a general idea of which ones are lower energy, which ones are higher energy.
Next one.
Yeah. Okay, so when we think about an atom and we want to talk about the electrons that are part of this atom, there's two main models that you guys have that explain, that explain the electrons in an atom. So that's the Bohr model and the quantum model. And there's very distinct, you know, there's large differences between these two models. So I want to talk about the differences. Firstly, the Bohr model. In the Bohr model, the electrons reside in orbits. If you guys remember, those those circles around the nucleus are orbits. And in the Bohr model, electrons are in those orbits. They're circular paths around the nucleus. And so if you put an electron in one of those circles or orbits, then there's a specific distance that that electron is from the nucleus. And so it turns out that that isn't exactly as accurate as it may seem. So what the quantum model says is, electrons are actually located in orbitals. And these are regions of space defined by electron wave functions where electrons have a high probability of being located. So it says, there's this high probability that this electron is in this density or this cloud of area. But, there's always that little bit of uncertainty that it may not be there. And that's something called the Heisenberg uncertainty principle that says that there's only this probability of that, a high probability that an electron is in a certain place, in a certain orbital at a certain time. So Bohr model orbits, quantum model orbitals. Now we talk about quantum numbers in terms of Bohr model. Well, the Bohr model really only tells us one of the four quantum numbers, and that's going to be n, because it only tells us what is the energy level of a certain electron. So you can say, okay, it's an n equals 1, it's an n equals 2. But when you talk about the quantum model, we have three quantum numbers, 4 if you want to include m sub s, that are, we can describe the location, energy, and orbitals of certain electrons. And so the quantum model is a more precise kind of, it tells you all the 4 different quantum numbers. We can describe electrons better with the quantum model. The next thing that's very important, so important that it's in red, is that the Bohr model treats electrons as if they were particles moving in a circular path, whereas the quantum model describes electrons as waves. So you guys remember the Schrodinger wave function. The wave is located in specific regions of space. And so that's a big differentiation, is that the Bohr model is particles, the quantum model kind of looks at it as waves. Now, what about similarity? We have a similarity that both of them allow for quantization of energy. Now, so you can just imagine that both of these models allow for that, so that must be very important. What that means is that electrons move in steps of energy, kind of ladders, or you can think of it as stair steps of energy. They don't reside in any energy level in between, but rather these steps of energy. And lastly, the Bohr model. Uh, the Bohr model explains something called the light spectrum. And when they first discovered the Bohr model, or kind of this line spectra of hydrogen, uh, we saw when the electrons were emitting certain levels of energy, there were different colors that were being emitted. And so they saw that, okay, electrons are able to move from different energy levels to different energy levels, and that each time, like let's say it moves from 2 to 1, there's a certain color that's emitted. From 3 to 1, there's a different color. And so different absorptions or emissions account for different line spectrums in the colors. Whereas the change in energy of in the quantum model is in a change of wave function. So we might see a different shape, such as maybe an s orbital to a p orbital, or n equals 1 to n equals 2. We see differences in orbitals and shapes. Next slide. Okay, so I already said one of the equations that you should know, which is speed of light equals wavelength times frequency. So c equals lambda times v, or frequency. The second equation you should know is energy equals h times frequency. And I count this as one equation because you can kind of use the speed of light equation, or you can use the speed of light equation to derive this. But either one you want to memorize works. I prefer to memorize hc over lambda because that's more practical. Usually you're going to be given a wavelength and asked to be calculated the energy, or given energy and asked to be calculated a wavelength. So energy equals hc divided by lambda, where h is the Planck's constant, 6.63 times 10 to the minus 34 joules per sec, or joule times second. What do I want to say about this? You have to memorize this. The constant will be given. You don't have to memorize the constant, but you do need to memorize the equation. Next slide. The third equation that you guys should know is, could you click hide on that thing, Kevin?
Oh, I didn't realize you guys could see that.
Okay, so equations to know. The third one that I want you to know is the Bohr equation. Sometimes it's referred to in textbooks as the Rydberg equation. But what that says, anytime on the test you see, okay, an electron has jumped from n equals 2 to n equals 4, n equals 3 to n equals 1. Anytime an electron jumps from an energy level to a different energy level, and they ask you to calculate what is the energy associated with that jump or that change, you're going to use this equation. Change in energy equals negative r, which is given there, times 1 over n squared final minus 1 over n squared initial. And this sometimes they can ask you for a wavelength. So if you calculate this energy that's associated with a certain jump, then you might have to follow this equation up with the energy equals hc over lambda equation, and rearrange that to solve for wavelength. But yeah, this is another one of the equations. Next slide. And lastly, the Broglie equation. This one sometimes a lot of people forget about. I at least forgot about it until I was reminded. But the de Broglie equation, the main thing with this equation that's going to get students is plugging it in with the right units. So you might see that they'll give you a mass in grams, or they'll give you a mass in pounds, or they'll give you a velocity in miles per hour. But you can't just put whatever unit into these equations. You have to put the kilograms for mass, and you have to put meters per second for velocity. And only then will it give you the proper meters for wavelength. And h is Planck's constant. That's the constant, 6.63, blah, blah, blah. And yeah, just please make sure that if you're given grams, you convert to kilograms. If you're given pounds, you convert to kilograms. If you're given blah, 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 you convert to kilograms. And you convert to meters per second for velocity. Next slide. Okay, so next big chunk of info is about quantum numbers. And like I said before, quantum numbers are these numbers that are used to describe the location of an electron, or maybe the shape of an orbital that it resides in. And so there's four quantum numbers: n, l, m sub l, and m sub s. So what are the possible quantum numbers for n? Well, n can be any positive integer. 1, 2, 3, 4, 5, 6, 7, 8, all the way to infinity. And what n tells you is n tells you the energy level of an electron. And what else does it tell me? It tells me the size. It tells me the size of an orbital or a subshell. And then it tells me one more thing. I can't recall. But mainly it tells you the energy level and the size of an electron. So okay, n can be any positive integer. Cool. What about L? Well, L kind of depends on n. And I say that because L can be any integer from 0 all the way up to n minus 1. So it can be, let's take an example of n equals 3. Everyone look at n equals 3. It's the third row in this chart. If n equals 3, then L, I know it looks like a P, but that's just like Greek or something like that, but it's an L. We all call it L. If n equals 3, then L can be 0, 1, or 2. So you see that it goes from 0 all the way to n minus 1, n being 3, so 2, 0, 1, 2. So what is L? When you guys read L, I want you to think this is going to tell me the subshell, or this is going to tell me the letter. What letter is it? So is it S? Is it P? Is it D? Is it F? So L is going to tell you the letter. It's almost like N and L are working together to tell you exactly which subshell to go to. So if I tell you guys that N equals 3 and L equals 1, that should automatically in your head ring, okay, 3P. I'm in 3P. Because 0, when L is 0, that's associated with S. And that's on the next slide, but I'll talk about that in a second. Yeah, so then we go to M sub L. M sub L now depends on L. So we see that L depends on N, M sub L depends on L. So, okay, what is M sub L? Well, M sub L is pretty much every value between, every integer between negative L and L. So, again, looking at that example of n equals 3, we know that L can be either 0, 1, or 2. So, L, when L is 0, well, from negative 0 to 0 is just 0. Then if L is 1, then we go from negative 1, 0 to positive 1. And when L is 2, we go from negative 2 to negative 1 to 0 to 1 to 2. So we see that negative L to L for M sub L. And then lastly, we have M sub S. I don't want you guys to forget about that. It's just going to be either negative 1/2 or positive 1/2. And what that tells me is the spin of an electron. And I forgot to mention that M sub L will tell you the orientation or the specific orbital that we're talking about. So just to recap, N is going to tell me the energy level. L is going to tell me the letter or the subshell, so SPD. M sub L is going to tell me the orientation, or aka the specific orbital that we're talking about. And M sub S is going to tell me the spin, either negative 1/2 or positive 1/2. How do you tell if M sub S is negative 1/2 or 1/2? So we use this, what do I call it? Like this, like we just kind of use this, like I guess, norm that if an arrow or an electron is pointed up, it's going to be positive 1/2, and if it's down, it's negative 1/2. But there's it's a little deeper than that in reality, and a lot of times we don't exactly know if it could really be either plus or minus, but for you guys, I want you to know that if it's up, it's plus 1/2. If it's down, it's minus 1/2. But just know in your head it's a little deeper than that. And if you want to know, go ahead. I just don't want to confuse people. Next slide. So yeah, like I said, L, I want you guys to think of what letter. So you see that when L is 0, it's 1s, or S. When L is 2, or sorry, when L is 1, it's P. When L is 2, it's D. And when L is 3, it's F. And so N and L work together to tell you exactly which subshell to go to. So if I say everyone, N equals 3 and L equals 2, what that means is 3D. I'm talking about the 3D subshell. Everyone, N equals 2 and L equals 1, that should be 2P. And so these two things work together to give you the number and the letter, the number and the letter. So just remember N and L work together in that way. Next slide. So this is just another diagram that kind of shows you that when N equals 1, possible L values, when N equals 2, possible L values, when N equals 3, possible L values, and it's just kind of showing you that the higher N you go, the more L value possibilities and M sub L value possibilities we have. So again, just staying consistent, if you look at N equals 3, we see that when L is 2, M sub L can be -2, -1, 0, 1, and 2. And so those are the specific orbitals. Next slide. Okay, so I've been talking about these orbitals for so long. What the heck is an orbital? What does it look like? And so you need to know what an orbital looks like. What is the shape of an orbital? And so there's 3 main orbitals that you kind of have to know the shape about. And I want to say 2 main orbitals because they don't really ask about D as much. But I want you guys to know S and P for sure. So the S orbital, it's very easy. It's just like a sphere. I see someone said grape. Yeah, it's like a grape. And the bigger, the larger energy level you're at, the larger your grape or sphere or orbital is going to be. So yeah, you see that 2s is larger than 1s and 3s is larger than 1s. That's really it. Now what about P? P looks like a dumbbell. P is like a dumbbell, and if you recall, there's 3 possible M sub L values when L tells you that it's P. So if L is 1, we know that M sub L can be -1, 0, or +1. I'm going to repeat that. If L equals 1, then M sub L can be -1, 0, and 1. So shouldn't there be 3 different orbitals? Yes, you're exactly right. There should be 3 different orbitals. And these 3 different orbitals are arranged in such a manner that they're as far away from each other as possible. So we see that one p orbital is along the x-axis, and we call that px. Another p orbital is along the y-axis, and we call that py. And the last one is along the z-axis, which is pz. So you just know that there's 3 p orbitals for, the subshell, and then we go to the d orbital. The shape of that kind of is usually like a 4-clove kind of thing, but sometimes it can be, if you look at the z² axis, sometimes it can be a dumbbell with a circle kind of circling it, with a ring circling it, but just know these shapes. Next slide. Okay, so that's it for my part of the presentation. But okay, Kevin, are we doing breakout groups?